Hi everyone. In this video, we'll cover a summary of the various integration methods we've discussed so far in this course. In particular, we'll review each of those methods. We'll develop strategies for selecting a reasonable method of integration for a given interval, and then we'll apply sort of that selection strategy to some selected integrals. So far, we've discussed four main methods of integration. We've discussed U substitution, we've discussed integration by parts, we've discussed trigonometric substitutions, and we've discussed partial fractions decomposition. We'll first go through and review each of those in turn. Beginning with U substitution. U substitution is helpful when we see an integrand which contains a function and almost the derivative of that function sitting inside the integrand, or entirely the derivative, but we can make it work if it's almost the derivative with just a constant issue. Now, for each of these methods, we're going to look at a quick example, but we are not going to fully work out those examples. Hopefully, we'll sort of discuss how we can make the U substitution, and for practice, you can complete the integral on your own. So in this case, when I first look at this integral, I'm looking for perhaps a function and its derivative, and I see functions like cosine and natural log and x. And just looking at those, none of those are derivatives of the other, right? The derivative of x is not cosine, the derivative of natural log is not cosine. But if I look at this for a moment, I might recognize that I could actually rewrite this as the integral of 1 over x times cosine of natural log of x. So that's just algebraically rewriting the integrand, right? I haven't actually done any calculation. I've just algebraically rewritten the integrand. And now I see the functions natural log of x and 1 over x. And so I know that the derivative of natural log of x is 1 over x. And so now I start thinking I could make a U substitution. So if I let u be natural log of x, then my du dx would be 1 over x. And I could then make the U substitution, which should transform this integral into the integral of cosine of u du. From there, you can find the antiderivative in terms of u and then substitute back in for the original variable. So again, in this case, U substitution was very helpful because I was able to identify a function and its derivative sitting inside my integrand in an appropriate way. Now, the next method of integration we discussed was integration by parts. Integration by parts is helpful when we see an integrand which contains a product of two functions, one of which gets simpler with differentiation, and the other which at least doesn't get any worse with integration. So if we look at this example, we see an x squared times an e to the 3x. So our integrand is a product of two functions. The function x squared will get simpler as I differentiate it. The function e to the 3x, as I integrate it, won't really get any worse. I'll pick up some constants out front, but it really won't get any worse. So I started to think this is probably a pretty good candidate for integration by parts. So to set this up, right, I'm going to call u my function which gets better with differentiation. So that should be x squared. That means that u prime will be 2x. V prime will be my function which doesn't get any worse with integration. So that'll be e to the 3x. And so to get v, I'll take an antiderivative. That'll give me 1/3 e to the 3x. And now I can apply the integration by parts formula. So the integration by parts formula tells me that this should be equal to u times v minus the integral of u prime v. Yes, u prime v. And so I'll pick up a 2/3 x e to the 3x dx. Now again, the integration by parts formula is not a guarantee that we'll immediately get the answer. What it's doing is it's exchanging our original integral for another integral that's hopefully easier. Now, if we look at this, we still can't directly compute this integral just immediately. But when I look at this, this is certainly better because now I have an x here instead of an x squared. And so now I could again apply integration by parts, this time to this integral, to eventually simplify the entire expression here and to get a closed form for the integral of x squared e to the 3x dx. You should be able to complete this by integrating by parts once more. The third method of integration we discussed was trigonometric substitution. And trigonometric substitution was helpful in the particular case that our integrand involved a factor of the form some constant plus a constant times x squared, some constant minus a constant times x squared, or some constant times x squared minus some other constant. So for example, if I look at this integral, the integral of square root of x squared minus 25 over x, I see that sort of term sitting here in the numerator, this x squared minus 25, and that makes me think that this may be a candidate for trigonometric substitution. In particular, because it's of the form x squared minus 25, I would guess that the best trigonometric substitution would be to set x equal to 5 secant theta. Now, if I do that, my dx will become 5 secant theta tangent theta, d theta. Derivative of secant theta is secant theta tangent theta. And now I can transform this integral. When I plug in to this integral, oops. So I'm now going to substitute everywhere I see x, I'm going to plug in 5 times secant of theta. Now, when I do that, I'm going to end up with an integral. I'm going to end up with 5 times the integral of tangent squared theta d theta. Okay. So again, I've sort of skipped some steps here. You should be able to check this. Essentially, you plug in here, this whole expression in the numerator is going to simplify to 5 tangent of theta. In the denominator, you're going to have a 5 secant of theta. And then over here, you're going to have a 5 secant theta tangent theta. And so the 5 secant thetas are going to cancel, and you're going to just be left with a 5 tangent theta and then another tangent theta hanging out over here. Now, we won't go all the way to the end here, but you might wonder, how on earth do I integrate tangent squared theta? Well, there's actually a nice little clever trick here. If I just rewrite tangent squared theta using the Pythagorean identity as secant squared theta minus 1 d theta, then what happens is I know the antiderivative of secant squared. Secant squared is the derivative of tangent. So this is 5 tangent theta minus 5 theta plus c. Now, I'm not entirely done because I need to convert back in terms of x. So for this theta here, I can actually just directly solve here. I'll get that theta is equal to secant inverse of x over 5. But for this tangent theta, I will have to draw a reference triangle. And again, you should be able to complete this problem. I would encourage you to try that. And if you're stuck, you come talk to me. But again, for trigonometric substitutions, what I'm really looking for are sort of those specific indicators where I have a term in my integrand that's of the form x squared minus something, or x squared plus something, or maybe a constant thrown in front of the x squared. Those are sort of indicators that trigonometric substitution may be an appropriate method to try. The final method of integration we discussed was partial fractions decomposition. Partial fractions decomposition is helpful when your integrand is a rational function in simplified form, meaning that the degree of the numerator is less than the degree of the denominator, and any common factors between the numerator and denominator have been eliminated. So, for example, in this case, we have 3x divided by x squared plus x minus 2. And so in this case, we want to use partial fractions decomposition to try and rewrite this integrand. So the first thing I want to do is take 3x divided by x squared plus x minus 2. And the first thing I want to ask myself is, what is the form of the denominator? So in this case, I have a quadratic, but it is reducible. I can factor it. So I can actually factor this as x plus 2 times x minus 1. And so now I know that my denominator is a product of distinct linear terms. And so I'm going to attempt to rewrite this in the form a1 over x plus 2 plus a2 over x minus 1. Now, in order to find a1 and a2, I'm first going to multiply both sides by my denominator here, x plus 2 times x minus 1, x plus 2 times x minus 1. So on the left-hand side, I will be left with 3x. On the right-hand side, I'll be left with, so multiplying into this first term, I'll be left with an a1 times x minus 1. And then multiplying into this term, I'll be left with an a2 times x plus 2. So that gives me that 3x is equal to, again, this is a problem we've seen before, a type of problem we've seen before, so I'm going to work through it rather quickly. But I should end up with an a1 plus a2 times x plus a2, sorry, plus 2a2, so 2a2, and then a minus a1 as my constant. So looking here, I see that I should have a1 plus a2, that's my coefficient of x, that should be equal to 3. And then my constant term should be 0 because I don't have a constant term over here. So 2a2 minus a1 should be equal to 0. Now to solve here, I'm actually first going to solve this for a1. If I add a1 to both sides, I get 2a2 is equal to a1, or a1 is equal to 2a2. Now I'm going to plug that in up here. So where I see a1, I'm going to plug in 2a2. So this gives me that 2a2 plus a2 is equal to 3. And that's the same as saying 3a2 is equal to 3, which tells me that a2 is equal to 1. Now that I know that a2 is equal to 1, I can plug back in here, and that gives me a1 is equal to 2. And so now, going all the way back to my original rewriting, I now know that my integrand can be expressed as 2 over x plus 2 plus 1 over x minus 1. Now, why is that helpful? Well, now, instead of integrating 3x over x squared plus x minus 2, I can instead just integrate this function, which is much easier to find an antiderivative of. So now, in this case, I'll instead take the antiderivative of this. Right, which is simply 2 natural log of x plus 2 plus natural log of x minus 1 plus c. So that's been a quick review of each of the methods of integration we've discussed so far, but all of this really raises a larger question. So anytime you have multiple ways of doing something, the immediate question that comes to mind is, well, how do I know which one is the best one to use for a given integral? Okay. The problem is there's really no one right answer, but we can sort of develop some rules of thumb or some guidelines for how we might want to deal with these. What I'm going to share with you is my thought process. Each mathematician has their own individual thought process, and as you do this more, you will develop your own. Part of it is based on personal preference. I find U substitution easier than integration by parts. Therefore, I want to try and use U substitution as often as possible over integration by parts, even if both of them might work on a given problem. So again, some of this is personal preference, but I'll share with you what my thought process is. I almost always start by asking, will U substitution work? I like U substitution. I think it's helpful. I think it's really when you can just choose the right U and the integrand collapses down, you have it's just really beautiful. It's really nice. That's usually where I like to start. If the answer is yes, U substitution works, then great. I'll do U substitution. If U substitution doesn't work, then essentially I'm going to sort of branch out into one of the other three methods. Okay. And essentially, I'm going to think about doing this in the following way. I'm going to sort of ask myself, well, is it a rational function? Okay. If U substitution won't work and it's a rational function, I might then wonder if partial fractions decomposition would help. If it's a rational function and partial fractions decomposition isn't going to help, I might ask myself, do I see a bx squared a b squared x squared minus a squared, or do I see a b squared x squared plus a squared, or do I see an a squared minus b squared x squared, right? Do I see any of those things that would tell me that this ought to be a trig substitution? Okay. If I see one of those things, then great, I'm going to try trig substitution. If nothing else will sort of work and I have a product of things sitting in my integrand, then I'm probably just going to try integration by parts and see where it takes me. Okay. So if all else fails, I'm going to try integration by parts. Now, by no means is this a foolproof system, right? You may end up doing an integral a way that in retrospect you decide is harder. But this is just generally sort of my thought process. I'm always first looking for U substitutions. And then if that fails, I'm looking to see if there are special forms that might indicate to me a partial fractions decomposition or a trig substitution. And then if I don't see any of that, I'm going to try integration by parts. Now, again, the reason I emphasize with integration by parts that what it really does is it swaps one integral for the other. Now, as you do this more, there's certainly integrals that I look at and I just immediately go, oh, that's an integration by parts, because I have about a 20-year head start doing calculus on you. So, right, in 20 years, I've seen a lot of calculus problems. A lot of that has become muscle memory for me. So if I see the integral of x cosine of x, I don't even think through this process anymore. I just know that's an integration by parts. But as you're developing that experience, you may sort of want to think through it like this. So if I have the integral of x cosine of x, I'd say first, will U substitution work? No, doesn't look like it. Is it a rational function? No, x cosine of x is not a rational function. Do I see any of these special forms sitting in there? No, not in x cosine of x. All right, let me try integration by parts. Okay. So again, that's sort of generally the thought process I work through, and that I encourage you to try and work through. If you work through the whole process, you don't think anything's going to work except integration by parts, you sit down to do integration by parts and it still isn't working, well, two things are possible. If it's a homework, maybe you just haven't seen something, right? But in the wild, right, if you just find some integral laying around, right, there's no guarantee that any of these methods will work. There are integrals which do not have nice closed forms. So for example, the integral of e to the x squared dx, this does not look like a bad function, right? This looks like a perfectly nice function. But it does not have a nice closed form that's expressible in terms of the normal functions you're used to thinking about. So again, even nice functions may not always have nice antiderivatives that can be written in a closed form. All right, the other thing that makes this hard is that there's not always just one way to find a particular integral. So I want to finish up this video with this integral. So we're going to look at this integral, the integral of x divided by x squared minus 1 dx. And we're going to actually see that we can use 3 different integration methods to find this integral. So if I'm working through my process, right, the first question I would ask myself is, do I see a function and almost its derivative? Well, yes, I see x squared minus 1 and I see x. So one way to attack this problem is by doing a u substitution. So if I perform a u substitution on this integral, I'm going to let u be x squared minus 1. My du dx will then be 2x. And then once I make the u substitution, I will end up with the with 1/2 the integral of 1 over u du. And now here, now the antiderivative is very simple. It's just natural log, or 1/2 natural log of u. I get 1/2. I get 1/2 natural log of u plus c. And then I remember I made up u, so I need to substitute back in. This is 1/2 the natural log of x squared minus 1 plus c. All right, very good, right? It's a perfectly good way of doing this. But let's say for some reason I didn't see the u substitution, okay? And so then I sort of walk myself into the next method, and I say, well, this is a rational function. Maybe I could do a partial fractions decomposition. Now, I'm going to sort of give away part of this here. You can check this on your own. If you look at this, the denominator factors as x minus 1, x plus 1. And you can rewrite this using a partial fractions decomposition as 1/2 divided by x minus 1 plus 1/2 divided by x plus 1. And so having done the partial fractions decomposition, now if I want to integrate, pull that 1/2 outside of the integral. And now this is 1/2 natural log of x minus 1 plus 1/2 natural log of x plus 1 plus c. Now, you may be concerned. Here, we got 1/2 natural log of x squared minus 1 plus c. And here we got 1/2 natural log of x minus 1 plus 1/2 natural log of x plus 1 plus c. Now, there are a couple of reasons not to be immediately concerned. The first is that these c's could be different, right? We could have different constants of integration, and perhaps these two things just differ by a constant, right? So it's always possible, right? Antiderivatives are not unique. There's a whole family of antiderivatives for any given function. So possibly these two things just differ by a constant, but it's sort of hidden. But the other thing we have to remember is that you can have multiple expressions for the same function. And in fact, that's exactly what's going on here. This and this really are the same. And we can see that if we just remember a couple of rules of logs. So if I were to take this expression and factor out the 1/2, and then recall that natural log of a plus natural log of b is the same as the natural log of a times b. So this is really 1/2 times the natural log of x minus 1 times x plus 1. But x minus 1 times x plus 1 is just x squared minus 1. So really, these two were the same, but just written in slightly different forms. Okay. So again, in this case, U substitution or partial fractions decomposition both give the same answer. But what if I didn't think about U substitution or partial fraction decomposition? And what if I looked and said, oh, I see an x squared minus 1. That sort of looks like one of the forms that I might be able to use a trig substitution on. So my third option is to think about a trig substitution. Now, I have an x squared minus 1. So that's going to suggest to me that I want to make the substitution x is equal to secant theta. If I do that, dx is going to be secant theta, tangent theta, d theta. Okay. And this integral is going to become the integral of, so my x is secant theta divided by secant squared theta minus 1 times my dx will become secant theta tangent theta d theta. And now this secant squared theta minus 1, that's just going to become tangent squared theta. So this becomes the integral of, so I'll get a secant and a secant. That's going to be a secant squared theta. This will be a tangent squared theta in the denominator, but I have a tangent theta here. So I'll just end up with a tangent theta in the denominator. Now, if I look at this, I might go, well, that looks sort of complicated. I could try to write this out in terms of sines and cosines, but actually don't have to go quite that far. I can actually do a U substitution on this because I see a tangent theta and I see its derivative, secant squared theta, sitting there. So if I let U be tangent of theta, then du d theta is secant squared theta. And this becomes the integral of 1 over u du. Now, with that integral of 1 over u du, okay, I'm now ready to actually start calculating some things. So this can become natural log of u. Then I have to remember that my u was tangent of theta. So this is natural log of tangent of theta. But now I still have to remember, this wasn't even my original variable. I made that up, right? So I have x is equal to secant theta. I need to draw a reference triangle. Okay, so if secant theta is equal to x, in this case, x over 1, all right, is that? And secant, it's 1 over cosine, so it's hypotenuse over alternate. So my hypotenuse will be x, or sorry, hypotenuse over adjacent. My adjacent side will be 1, and by the Pythagorean theorem, this will be x squared minus 1. So then tangent theta, which is opposite over adjacent, will be what? It will be square root of x squared minus 1 divided by 1, or just square root of x squared minus 1. And so, at the end of the day, this becomes, substituting back in, natural log of, and I'm sorry, once I started integrating here, I should have picked up a plus c. This becomes natural log of square root of x squared minus 1 plus c. Okay. And this is our final answer. But again, you're going, wait, that's not what we got in either of the two other cases, but it is equivalent. To see that it's equivalent, consider that we could rewrite this square root as all of this to the 1/2 power. And anytime you have the natural log of a to the b, that's equal to b times the natural log of a. So you can basically bring this exponent down outside. So this really is equivalent again to 1/2 natural log of x squared minus 1 plus c. So here you've seen many different methods for attacking the same problem. And what this should really illustrate to you is that the question isn't always, what's the right method or the best method, although certainly we do care about that. But often there are many methods that may work, and you just need to choose one that you like using the best. That's always, again, for me, it's U substitution when I can do it. So I sort of try to default to U substitution if I can. If that is, causing some problems or it's not working for whatever reason, then I may switch to some other method. But you need to choose a method that you are really comfortable with, make that sort of your primary method, and then, if that works, great. If not, we'll move on to another one. So that concludes the work for this video. Now you're going to have a lot of opportunities to practice this. So in particular, I'm going to give you a number of different assignments and different types of assignments that are going to test your ability to do a couple of things. One is to actually implement different methods of integration, but the other is to just select an appropriate method to try first. Again, for those problems, I'm going to ensure that there's really only one method that is likely to work. But again, you want to start being able to quickly recognize what's likely to be an integration by parts problem versus what's likely to be a trig sub problem versus what's likely to be a U substitution problem. So you're going to have lots of opportunities to practice that in the upcoming assignments. As always, if you get stuck, if you have difficulty, please do reach out.